Hi everyone. So today we're going to continue talking about maximal ideals, and then towards the end of lecture we'll start talking about ring homomorphisms. So just as a reminder, last time we had this result. So we were talking about prime ideals, and we had a result that R mod A was an integral domain if and only if A was a prime ideal. And today we're going to see an analogous statement, but for maximal ideals. And right at the end last time, we saw the definition of a maximal ideal. So I'll just repeat it in case it was forgotten. So if R is a commutative ring and A is some proper ideal in R, so it's not equal to the entire ring, then we're going to say that A is maximal if any time you write another ideal that contains A, and it's also inside of your ring, then you either have that B is equal to A or B is equal to R, right? So it's not possible to put another ideal in between A and the full ring. So if that's the case, then you'd say that A is maximal. And we'll see that a lot of times proving a maximal ideal will end up involving like showing that this intermediate ideal B contains the element 1, because that will force it to be equal to R. And we'll see an example of a proof that looks like that today. Okay, so now I'm going to give you the definition of a field. So if you were in 540 with me last semester, we saw a definition of a field from axioms, and there was like, I forget, 8 axioms or something like that, like a long list. And now now that we have like the language of rings, we'll be able to get a much simpler definition. So let's see how that goes. So a field is a commutative ring with unity such that every non-zero element is a unit. Okay, so what does this mean? Let's unpack this statement. So the fact that it's a commutative ring means that we have an addition and a multiplication operations such that both of those are commutative, and we have a multiplicative identity, and furthermore, every element has a multiplicative inverse. And then because it's a ring, we also have that with respect to addition, it's a group, and we have these distributivity laws. Okay, so that's what a field is, and the way that I think about this is like a field is a ring where you have the power to add, subtract, multiply, and divide now. And you have multiplicative identity and additive identity. Okay, so some common examples that you are familiar with are the complex numbers, the rational numbers also form a field, the real numbers, and Z mod P is also a field. Okay, are there questions about this definition? Okay, so I'm going to give you a proposition and give you time to think about how to prove this. So the statement is that fields are integral domains. So if you have a ring R and it's a field, then that implies that it is also an integral domain. So I'll give you a few minutes to think about how to prove that, and then we can discuss. Okay, let's go over the proof of this. So to show that this is an integral domain, we need to show that it has no zero divisors. Meaning that if I have a product of two elements, A, B, and that equals 0, then either A equals 0 or B equals 0. Okay, so this is what we need to show. So let's assume that AB is equal to 0. If A is not equal to 0, so if A is equal to 0, then we're done. If A is not equal to 0, then since we're in a field, it has a multiplicative inverse. So there is some element called A inverse, such that A inverse times A is equal to 1. So let's just take our equation AB equals 0 and multiply both sides by A inverse. Okay, then on the left, this gives me B, and on the right, I get 0. Okay, so then that finishes the proof because we ended up in the situation that supposing A was not equal to 0, then B is equal to 0, and so that means that there cannot be any 0 divisors. So that finishes the proof. Are there questions about that? Okay, so now let's see the theorem. So this will relate fields and maximal ideals. So let's let R be a commutative ring with unity. And we'll let A be an ideal of R. Okay, then the statement of the theorem is that R mod A is a field if and only if A is a maximal ideal. Okay, is this statement clear? Okay, so let's see how to prove this. So since it's an if and only if statement, we're going to have to prove both directions. So let's start off with the forward direction. So we'll suppose that R mod A is a field. Okay, so then we want to show that A is a maximal ideal, so we need to show that it has this property that if there's some other ideal B containing it, then B is either A or the entire ring. So let's let B be an ideal such that B contains A and it's inside of the whole ring. And let's suppose further that B is not equal to A, all right? So B properly contains A. So then what we need to show is that B equals R, and that will enable us to conclude that A is a maximal ideal. Okay, so let's consider some element that's in B but not in A. So we'll call this thing little b, and it comes from B backslash A. Okay, so then now we're going to look inside of this quotient ring, which we've assumed is a field. So let's consider the element B plus A inside of the quotient R mod A. Is this 0? Is this the additive identity in this ring? No. Why? Yeah, so since B is not in A, this is not equal to 0 plus A, which is the additive identity. In R mod A. Okay, so since we have found a non-zero element of R mod A, and R mod A is a field, we are allowed to invert it. So there is a multiplicative inverse of this element, B plus A. So let's call it C plus A. So we'll let C be an element of R with B plus A times C plus A equal to A, or sorry, 1 plus A. Right, because this is the multiplicative identity inside of this ring. So saying that B plus A has a multiplicative inverse just means that there's something that we can multiply it by to get the multiplicative identity. Okay, so let's just write this out. So this is, by definition, this is equal to BC plus A. So this is equal to 1 plus A. And let's observe that since B is an element of our ideal B, we also have that B times C is an element of B. Okay, why? Because B is an ideal, so I can multiply anything in B by anything in the ring, and I stay inside of B. Okay, so we have that BC is in B. And by this line, we know that 1 minus BC is an element of A. Do you all agree with me on this one? Okay, so BC is an element of A, and A is a subset of B, so that means that 1 minus BC is an element of B as well. Okay, so just to summarize, we have 1 minus BC inside of B, and we have BC in B. So that means that 1 is an element of B because B is closed under addition and subtraction. And so that means that we win. So that means because, so once you get 1 inside of your thing, you win, right? Because that means that this is, that B is equal to R. And we can, if you like, we can go over this argument again. Does anyone want to see this? Yeah, okay, so if 1 is in B, we can take anything in R. So, okay, so let's elaborate on this. So if 1 is an element of B, then given any R in R, R times 1 is an element of B, because I can multiply things from the ring on things in B and stay in B. And so that means that R is a subset of B. And we already know that B is a subset of R. Okay, so this finishes the first half, so we conclude from this that A is maximal. Are there any questions about this part? Yeah.
Could you just go back over why 1 minus BC is in A?
Yes, okay, so from this equality, just by the definition of multiplication of cosets, we have that BC plus A is equal to 1 plus A. And then by like properties of cosets, this means that, let's see, 1 minus BC plus A is equal to A. And that happens only when this element is inside of A. Yeah. Other questions? Yeah.
At the start, we assumed that B is not equal to A, right?
Yeah.
Isn't that only like half of the statement? Because doesn't it also say like B could equal A if B is not equal to R?
Okay, yeah, so So right, so when we had a max, like what is our definition of a maximal ideal? We say, okay, what if we have a chain like this? B contains A and B is contained in R. Then we need to show that B is either equal to A or it's equal to R, right? So if B is equal to A, then we're done. Right?
Oh.
So let's just assume that B is not equal to A and then show that it's equal to R. Yeah. So this is like, this is kind of going like way back, but to like, if we want to prove a statement that's like prove P or Q, it's enough to assume not P and then prove Q. Yeah. Other questions before we do the other half? Yeah. Why a B times C is what? Yes, because, okay, so B is an element of B, and since B is an ideal, we can multiply by anything in the ring and stay inside of B. So yeah, C is then just like some ring element, we're multiplying it times B, so then this is an element of B. Yeah, I feel like this proof, like, it uses all of the assumptions, right? Like it hits like every single piece of what we've been looking at recently. Yeah.
Well, just to be clear, when we say A, is it like every possible ideal that is not R inside R?
Sorry, can you repeat that?
Like A is all ideals in R? Or A is like for all ideals?
A is like some fixed ideal such that R mod A is a field.
Okay.
So like as an example to keep in mind, we were looking at the complex numbers mod the ideal generated by x squared plus 1. Or sorry, this should be the real numbers. So this is the complex numbers. So this is like, if you wanted to think through this proof in like a specific example, this is like something that you could think about. Yeah. And we'll see, I guess we'll see later a proof why this is a maximal ideal. Okay, other questions? Shall we do the reverse side? Okay, so for the reverse, we're going to suppose now that A is a maximal ideal. And then that means that we need to prove that R mod A is a field. Okay, so what is a field? It's a commutative ring with unity in which every non-zero element is a unit. Okay, so if R is commutative, then R mod A will also be commutative just by the way the multiplication was defined. And the unit in R will still be a unit the unity in R will still be the unity in R mod A. So this is a commutative ring with unity. And so then to prove it's a field, we just need to show that non-zero elements have multiplicative inverses. Okay, so to that end, let's let B be an element of R such that B is not an element of A. Okay, why? Because then B plus A is a non-zero element of R mod A. So we need to show that this element B plus A has a multiplicative inverse. So how we're going to do that is we're going to create an ideal that definitely contains A, and also contains some other stuff. And so that will show that then since A is maximal, that ideal has to contain 1. And then we'll use that 1 in a clever way to construct the multiplicative inverse of this B plus A. Okay, so I'll show you what that ideal is. So let's let B be equal to the set of, so we have our little element B. We're going to take B times R's plus A's such that R is in R and A is in A. Okay, so this is an ideal of R that properly contains A. So maybe we should take a moment to convince ourselves of this. So why is it a subring? Well, if I add or multiply elements of this form, then they'll remain of this form, right? Why does it contain A? Well, I could take this R to be 0, and then all elements little a in A are in this ideal. And if I multiply by any ring element on an element that looks like this, then it will be of the form B times R plus A. Does that make sense? Do we believe this claim that I just talked through? Yeah.
Sorry, what's the element that, like, in B but not A?
This little b. Yeah. Yeah. So that's what this little b is, the same little b that's here.
So that's why it's like a proper.
Yeah. Okay, so we have this chain. Then, since A is maximal, that means that B is equal to R, and so 1 is an element of B. So that means that we can write 1 as being equal to B times, let's go back. So 1 is an element of B. So that means that there's a way to write 1 as B times R plus A for some R in R and some A in A. So I'll write this as R prime plus A prime for R prime in R and A prime in A. Okay, are we on board so far? Okay, so now we actually have, so what have we been looking for? We want the multiplicative inverse of this thing. And I claim now we have it. So let's do B plus A. Let's multiply this by R prime plus A and see what happens. So B plus A times R prime plus A is equal to BR prime plus A. Okay, so that's just by the definition of multiplication in the ring of cosets. And then I'm just going to pull out from A an A prime. Right, because, okay, so what just happened? Cosets absorb elements that are inside of them, and so I can also pull them out. Okay, but this element is equal to 1. So that finishes the proof, because now we've shown that R prime plus A is the multiplicative inverse of B plus A, which shows that elements of R mod A, or rather non-zero elements of R mod A, are invertible. And that was all that we needed to show that this was a field. So that completes the whole proof. Are there questions about this half? Is that too small to be yeah, it's too small. Are there questions? Yeah.
Why is B multiplication?
Okay, because, so first of all, B contains A because I could set this little r equal to 0. And so then I have all the elements of A inside of B. And then it properly contains it because if I put this to 1, then B plus A, let's say, this is not an element of A. Why? Because if it was, then B plus A minus A, which is B, would be in A, but that's not the case because B was selected to be in something that's not in A. Other questions? Yeah.
Can you quickly explain why the other field properties don't follow clearly?
Yeah, so okay, so we said a field was a commutative ring with unity in which every non-zero element has a unit. We only showed that non-zero elements have units. So why is it commutative? And why is it why does it have a unity? Okay, so the commutativity, so this just says that the multiplication is commutative, and the multiplication is defined like A plus A times B plus A is equal to AB plus A. But this multiplication is commutative, so I can commute these two things. And so that shows that the multiplication in the quotient is commutative. And then why does it have a unity? So if 1 is the unity in R, then we should have that 1 plus A is the unity in R mod A. And like, why is that? So let's just like stare at this equation again, right? If one of these things is 1, then this will be 1B, which is just B. Yeah. Other questions? Okay, so I'm going to give you a minute to prove a corollary. So here's the statement of the corollary. So this says that all maximal ideals are prime ideals. So I'll give you a minute to prove this, and a hint is that this is like truly like a one-line proof, just using things that we've already proved. Okay, let's see how the proof of this goes. Okay, so let's let R be a commutative ring with unity, and a maximal ideal. Then we just showed that R mod A is a field. And previously in the lecture, we showed that fields are integral domains. And then last time we showed that if R mod A is an integral domain, then A is prime. Okay, is it good? Are there questions? Okay, I'm gonna now draw. Do you have a question? Wait, finite integral domains are what? So we proved today that field implies integral domain, right? We're not using the reverse direction. Yeah. Yeah. Okay, I'm gonna draw a picture to kind of just summarize like the types of things that we've looked at so far. Okay, so we started off the course talking about groups, which I'll draw as like this big circle. So this is groups. And for the sake of like comparing with rings, I'm going to only look at groups under addition. Okay, so this is like the most kind of general object that we've looked at so far. And then within that, you could look at abelian groups with addition. I don't think I made myself enough space for this picture. I'm just going to move it. Okay, so then inside of that, you know, we can add another operation called multiplication, and we get rings. And then within that, our rings can be, they can be commutative, or they can have unity, or they could be both. So these will be the commutative rings. And then these will be the ones with unity. Okay, and then among commutative rings with unity, inside of here, we have integral domains. And then within that, there's fields now. Okay, so this is like just a diagram of the things that we've studied so far. And then I'm going to make a corresponding picture on the right of like types of subrings. So among all subrings, we've mostly been interested in ideals. And so far, in the last two lectures, we've shown that within ideals, we have something called prime ideals. And then even within that, there's something called maximal ideals. And then the connection between these two is that are the theorems that we've proved the last two times. So A is prime if and only if R mod A is an integral domain, and A is maximal if and only if R mod A is a field. So I think this picture is just helpful for kind of like sorting out the concepts that we've seen so far. And as we go on, you may like add to this picture because there's going to be like more things that come up, more types of rings and more types of ideals that we'll look at. Are there questions about this picture? Yeah. Okay, yeah, so this line, each of these lines is like a theorem. So, so like R mod A is field if and only if A is maximal. And then this line is R mod A is an integral domain if and only if A is prime. Other questions? Okay, so in the last few minutes here, I'm just going to give you the definition of a ring homomorphism, and then we'll talk more about ring homomorphisms next class. Okay, so it's possible that you could guess the definition of a ring homomorphism. So a ring homomorphism and we'll denote it by phi from a ring R to S, is just some function from R to S such that, and what should our conditions be for this to be a ring homomorphism? Does anyone have a guess? Yeah. Yeah, so we just want it to preserve the operations. So we'll have that phi of A plus B for A and B in R is equal to phi of A plus phi of B. And then we also want that phi of A times B is equal to phi of A times phi of B. And this is like super common in math. So usually when you define some type of object that you're interested in, you'll also have an idea of a morphism between those types of objects. And typically you want the morphism to preserve whatever the structure is that you have. So in algebra, that's usually like the operations, but in other types of math, there might be like other structures that you want to preserve. Yeah. Yeah, so these are both rings. Okay, are there other questions? Okay, I'm going to stop there and we'll do examples starting on Monday, and then we'll get a bunch of properties of homomorphisms and some theorems too.